What's up, folks? In this supplemental video to my trees data structure video, today we're going to talk about graphs. And when I say graphs, I'm not talking about this. Stand by. This video is about to start. This is the Savage Scientist Ed right here. And I'm Uber and police car. Alright, so y'all already saw the intro. You already know who this is. But if you don't, this is the Savage Scientist Ed, governor of the state of Swampland. And today, like I said, this is a second part of my 5th video, and I didn't want to make that last video too long, so we're going to continue with nonlinear data structures such as trees. And the difference between a nonlinear data structure and a linear data structure like arrays and linked lists is that the data is in sequential order, meaning that if you have some 10 items, they all gonna appear as 10 items in a row. That's how the data structure is laid out, and that's what it's gonna look like. That doesn't mean that it's gonna look like that in memory. That's just the way that is just the logical layout of the data structure. So now it's time to talk about trees. God damn it, I'm gonna have to take that part out. No, I'm leaving it in here. So now it's time to talk about graphs. Graphs, it's kind of like a tree, except there's no root, and there's a few other things. So here's the index for this video. Go through my notes here, and let's talk about these graphs. And we're not talking about graph paper or any of that other stuff. Computer science graphs. So a graph in computer science is a data structure, a nonlinear data structure that doesn't have a root. So it would start at one arbitrary point on the graph, and it allows multiple links, multiple outlinks, multiple inlinks. It's just a lot of linking going on. So let me give you a few examples of a graph. So this is what I would call a non-weighted graph, or just a normal graph. Have you ever been on Facebook, Instagram, or YouTube, and you might see people linked together like friends, groups, all that stuff, the whole grouping thing? That is an example of using graphs. So what I have here is some of the people that's associated to my links on YouTube. If you click on my little system, if you go down, click down there, and you'll see a section on my YouTube page called The System. And what that is it's my suggested channel, or people who I'm associated with on YouTube. So let's take a look at the system here. So you see I have Barry, Gadget Goddess, Easy Computer Solutions, and a lot of other people. So my thing is, when you look at these links, you could learn a lot about the people I hang out with. So this is the same thing that Facebook does and other social media networks do. So they use this information to serve ads to you. So that's why this is important for social media. So now it's time to take a look at this YouTube example I was talking about earlier. So I'm going to use a graph to represent some of the common channels that I have featured on my YouTube channel, and the same thing on their YouTube channel. So let's take a look at it. So on the left of your screen, lettered from A to I, are some tech YouTubers whose content I enjoy watching, and also they may have mentioned me or I was participating in one of their streams. So now I'm about to represent this relationship as an undirected graph, and later I would explain what I mean by undirected graph. Graph nodes indicated by the circles, and the graph edges are the lines in between the two circles. I'm about to label these nodes A through I to represent the YouTube channels that I'm talking about. And you can look at this graph and cross-reference the YouTube channel with its corresponding node. For example, A is my channel, Savage Scientist. This orange colored line shows the channels that I'm linked to. So as an undirected graph, the lines just link the two nodes. But that doesn't mean that there's a link back from, let's say, from node C to A. So that's why it's good to use something that we call a directed graph. And what a directed graph is, it shows the direction that the link takes us. So a directed graph could be looked at as a one-way street. There's a one-way link between A and B, and A and E, A and D, A and C, and A and H. So the rest of the example is going to be similar to this. So now it's time for me to show the rest of the links and the rest of the connections on this graph. Now it's time to talk about node degree. And that's an important function of a graph because it shows how many links we have coming into our node and how many links we have leaving the same node. So I'm going to indicate that by this number with the backspace in the middle. So let's take a look at it. So I know you probably noticed node A has 5 orange links to other nodes. And you notice there are not any nodes going back into A. And those lines represent my channel. Those orange lines represent my channel and who I am, the Savage Scientist. And when you look at the in and out links, you'll see that my channel has 0 in links and 5 out links. And mostly everyone else has some number, 7666, until you get to node I. That is 4 links in, 0 links out. Because on YouTube, there's you have to actually expose that feature to share channels. And Jay William isn't showing any channels. So that's why there's 0 links out from his channel. So this is just to show you what a graph network looks like. Now it's time to talk about representation or graph representation as far as programming. And this is probably going to be the most technical part of this video. So the graph node is the basic element in the graph data structure. It has an integer value key, but it also, so that key could also be character like we used in the last example where we had ABC all the way to I. But in most cases, the key is going to be an integer value. And the data is of any type. So going back to my video on data types, that could be integer, float, Boolean expression, character strings, or even objects. This sample node has the key value 2, and you see how it has the circle? That's the standard notation for nodes in our graphs. Now it's time to look at the graph data structure. So implementation of the graph data structure could be done in many ways, but I'm going to use pseudocode as it saves time. In this simpler implementation, the graph data structure will have a node list called nodes and an edge list called edges. And you can see here that all our nodes are stored within the graph itself. And I think it's time for an example so I can show you how this implementation works. So we have 2 nodes in this graph, one node called A and one node called 2B. And the most important thing to look at is this link between A and 2B. So that is implemented through this thing called edges. So we only have one edge, so edges 0 would be this link, or the first edge, the first and only edge in the edge list. So if you look, it says from, so that'll be A, and 2 will be 2B. The weight will be 9. So now that we have our connection done between these 2 nodes, let's talk about the mode. If I set the mode to 1, that means that we won't have any edge value. If I set the mode to 2, that means we're going from source to destination. And if I set the mode to 3, that means that the source and the destination, it doesn't really matter because they're going to share the same edge value whenever you follow in this link. All right, so now that I went through some of the details on implementing these graphs, let's take a look at just different types of graphs. And I want to give you some examples of these graphs so you can have a good idea of what I'm talking about. So an undirected graph doesn't have arrows, as you can see in this example. Now I'm about to convert this into a directed graph by throwing some arrows on here. It's called the directed graph because the arrow shows the way data is traveling within this graph. So let's write in our nodes. Let's see, we have N1, N2, N3, and N4. And let's do our edges, E1 through E5. So without going through a formal definition of a cycle, it's basically a collection of nodes or vertices all adjacent and connected via some edges, and they form a cycle because you could start at one node and visit other nodes until you return to that same node. So in this example, you could use N4, N3, and that's a cycle. But there's another cycle in this graph too. Do you see it? So yes, it's indicated in this blue line. So you could start at N4, follow the 9 to N3, and then follow the 2 to N2, and then follow the 5 to N1, and then back at N4 with an 8. So that'll complete the blue cycle in this graph. So now I'm about to show you additional ways of representing these graphs. So the first representation here is called the adjacency matrix, and I could have did it with the channel thing earlier, but just imagine making the adjacency matrix that big. I know y'all probably wouldn't want to see that. So I have this simple graph, and let's do an adjacency matrix with this simple graph. So as you can see, I have on the X and Y axis, I just have the nodes labeled N1, 2, 3, 4 across the top and the bottom. If there's a link from one node to the other node, then I'm gonna put a 1. In order for me to mark a 1 into the adjacency matrix, there has to be a link between the two nodes. So let's look at it going from node N1 to N4. You notice there's a 1 under N4. That means that the direction of the graph goes from N1 to N4, and that you can't go back to N1 from N4 unless you go through N3, N2, and back into N1, and then follow that link. It's like a one-way street. It follows the direction of the edge. So let's move on to the next way of representing this. So, and another thing, this will be done with arrays. So this thing is going to take up a lot of space if you have 1,000 nodes. So that's why the list implementation that I mentioned earlier would be suitable for certain situations. So this is the weighted adjacency matrix. And what this is this is the same concept, except now instead of putting a 1, I'm actually putting a weight with that associated edge. And I want you to take a look at number 3. There are 2 links. Node N3 has 2 outlinks, and look at that 64. This is a good example of a traffic map or something. So if you see a 64 on the map, or if you see something with a value 64, you know that this is not the route you want to take. So going back to N4, there's actually a shorter route going the long way. So you'll go back and hit the 2, the 5, the 8, and that together is less than 64. So it looks shorter on the graph here, but in reality, it's definitely not the best choice. So next I'm about to do the incident adjacency matrix, or the incidence graph. So what that is the same concept, except we're gonna put all the possible values here. So if there's a link between 2 nodes, like let's see. So since there's a link between N1 and N4, its value is 8. N2 and N1 has a 5. N3 has 2 links. You have N2 with 2, and we have N4 with 64. That's that big one again. And N4 goes to N3 with the value 9. So the thing here that you should take from this is, if you have a sparsely populated graph, then it might be good to use the adjacency list for. And if you have something densely populated or densely clustered graph, then that's the time when you might want to use the adjacency matrix. And the adjacency matrix is just a collection of arrays, if you decide to implement it with arrays. I mean, they have all kind of ways to do this, but I mean, you could do it with a 2-dimensional array. There are a lot of ways, but if you use arrays, you're gonna take up a lot of space. So my next video is gonna be on hash tables. So until that video posts and I do my live stream, peace out.